is going to be an introduction to CCP estimation. And draws heavily on what Whitney and Bertel were saying. Sorry, I couldn't get around to the option stuff. Otherwise, we would have been able to link all three. But that's just the way it is. So, just to give you the standard kind of framework in which these kinds of problems are usually set up in, is the T could go out to infinity. There's a infinite horizon, could be an infinite horizon problem. Choosing between capital J, discrete choices. The choice set could vary over time. The reason I haven't bothered doing that is that just adds even more notation. You're choosing one of a bunch of mutually exclusive things. Again, you just set it up that way. You can always make things an exclusive choice by looking at each permutation separately. To keep it simple so that we don't have to think about non-parametric estimation to begin with, we'll just imagine that the state variables, the x's, that just come from a discrete set. And typically we think about that as being finite, not necessary. And as Bertel pointed out, the epsilons are usually thought of as coming from a continuous distribution with a density function. And that's what I'll do here too. And we almost always use logit, although that's not strictly necessary. We'll talk about that in a minute. There you get observations on the choices and also the states that people are in. We can relax that somewhat, but some of identification goes away if you start to think about states that are not observed. And so that's something that take quite seriously. There's a joint distribution for both the x's and the epsilons that drive this thing. So they're the underlying drivers, and then people make decisions on top of them. And we're going to appeal to, in this lecture, the conditional independence assumption, which Bertel introduced and with John really pioneered, I'd say, in assuming that there's a separation between what you observe and what you don't observe. In particular, that you get this decomposition that allows you to break up the transition of the state variables into things that only depend on the state variables, and the unobserved disturbances just to depend on current values of stuff. So just to complete it a little bit, we need to make sure that the utility function that the agent, or the optimization problem that the agent is solving is well defined. And so if it's an infinite horizon thing, well, you can't make stuff get too big near the end, otherwise it'll be bouncing backwards and forward between positive and negative infinity, and we don't know how to add those two numbers together. So to keep it really simple, we keep the expected value of the maximum, the epsilons bounded, and also keep the utilities bounded. And then the agent goes ahead and maximizes his problem by choosing these set of discrete choices. So that's the standard kind of way of moving forward on most of these problems. When we relax these assumptions, well, we then have to start thinking fairly specifically about the ways in which we relax them. There's something called, Bertel introduced this, will describe these, what sometimes gets called as the social surplus function, or the ex ante value function, which is just the value of the optimal value of the optimized problem for the agent just before he sees the next epsilon and moves forward. And also Bertel wrote down for you, so I was listening, the conditional value functions. So namely, what would you get from the systematic, what we call the systematic part of the utility, current utility, the U of X plus what happens if you do the optimal stuff. And then the thing that I'm going to be emphasizing today, and as part of the CCP estimation method, are what we'll call the conditional choice probabilities, namely, what is the probability when somebody is acting optimally, that they will choose, say, action J when we see the X's of the state variables. Now, this I've described an optimization problem, but John, in a way, introduced a way of thinking about games too just then. And this is the way people have thought about dynamic games when they're estimating them. They think about them in terms of each player optimizing relative to the other players in the game when the other players in the game are playing their part of the equilibrium too. So in this sense, we can extend dynamic optimization problems to dynamic games in a fairly straightforward way. So we've got I players now, and so now we're just superscripting everything by I, the actions that they take, and then we just lay out the decisions of all the players. And since we're going to be talking about best replies by an individual I to everybody else, it's almost as if everybody else is part of nature in the transition problem of the individual optimization problem that each individual is solving. So X now, the state variables, not just of one player, but all, say, the firms, because obviously each firm depends upon the capital of all the other firms, not the same way, of course. The less capital they have, the better it is for me. The more capital I have, the better it is for me too. So clearly, the different capitals of different firms count in different ways. And now we have a transition probability that says, well, what is going to happen to all the state variables in, say, this industry, conditional on what the state variables are now, and also what all the actions of the players will do in this period, taking account in a minute that they'll, of course, be doing stuff that's in equilibrium. When we look at the world, all we see are the equilibrium actions. So all we see is the data generating process from that equilibrium. We don't see off equilibrium stuff. And so in that way, we have to think carefully about what the equilibrium stuff that we don't see is the model in order to be able to, we'll say, identify and estimate the parameters of the model that we're looking at. So you can see how structural econometrics must rely very heavily on the economics in order to be able to get anywhere to say anything about counterfactuals. In any event, we also define the distribution of the transition of mixed period state variables, given what all the other guys do, because that's going to be important for what this guy thinks about doing. So that's why I subscripted that little J there to reflect the fact that Mr. I or Ms. I is taking the Jth action when everybody else is doing their minus I stuff. So in this setup, each person is thinking about maximizing not just a little U now, but this big U here. And it's going to depend on, notice, the actions of everybody else. What they do affects my payoffs. And so that's them affecting me, and that's my utility function that I'm going to get out of that. And so here is the analogy that to the single player setup. And we want to, we're thinking about the conditional choice probability of what I will do given what I have. That's the standard thing. And then I want to also define the probability of everybody else doing what they will do. That's the product of all their individual actions, because they can all see, as the data analysts can see, the X's, but none of them can see the epsilons that they each draw. And so that's the sense in which we're talking about Bayesian perfect market equilibrium.
Oh, Bob, just
yes.
So here, you're assuming simultaneous moves at every period.
Yes.
So if I move J, it won't affect what they're doing because they
correct.
Don't see what I'm doing.
That's correct. And suppose they could. now you'd have a sequential perfect information game. That would actually make it easier, wouldn't it? Because now I get to see the state variables of what everyone else has done. I'm going to move. And what's the transition function going to be? It's going to be what they do in the future. I will know, at least in the data, what those choice probabilities are. And so if we were talking about a perfect information game in which people move sequentially, well, then it would be almost exactly like a single agent game, except that you would have to take into account that you only get to move ever so often because these other people are messing up what you want the world to look like for yourself. And so that's the sense in which they will map in. So this is actually a little bit more complicated than that, because people are making simultaneous moves. That is, they're making their design on an electric car while somebody else is making their design on an electric car. You each do not want to know what the other person is doing. So it's not literally simultaneous, but it is a game of incomplete information, which often arises in this kind of setup. So these choice probabilities are going to be, just briefly, is an equilibrium if for an individual agent. So it's going to be a set of, it's just to be clear about this, it's an equilibrium, okay? I is solving this problem, and when I is solving this problem, given that all the other people are solving their problems that way too. Okay, notice how I've managed, how we can define the equilibrium just in terms of the x's, and this is analogous to what Berta was saying about getting those x's and epsilons back into the x value function, just getting back, pulling it back the x's. I've got to be solving my problem, okay? And when I solve my problem, I get one of my PJ in here, okay, or my PI in here. Given that everybody else is solving their problem in exactly the same way, when I substitute their P's into the, sorry, when their P's come out of them solving their problem, hence they get the D minus I. So that is how you can define the fixed point for a setup like this. And to see that this is analogous, or pretty much exactly the same as an optimization problem. You just interpret the U with this this function here, okay, and then the F with equation 3 here. So equation 3 is easy. This is the part where they're playing, where it looks as though they're playing nature. In fact, even in an individual optimization problem, when you're thinking about your budget constraint or the choices, of course, people affect what that constraint is. So this is almost exactly the same as it would be in an optimization problem. It's just that you're being very explicit about what people are doing here, whereas in an individual optimization problem, you're not. And over here, notice that you've just got this little U here, whereas this thing depends on both U and D, okay? It's got more arguments in it. So if you could identify this, that's not going to necessarily identify this. And typically, obviously, people make structural assumptions, functional form type assumptions about in order to be able to identify what's going on in the game. And if you're only seeing the actions and the states, well, then you are going to have to make assumptions along those lines, because this obviously has more arguments than this one, or make assumptions on other parts of the model to be able to do it. So I want to move on. Any questions before I move on? Just because I say I want to move on, you don't need, you can stop me if you want. So starting point. Basics, the basic starting point is, again, something that Bertel gave you, more or less gave you. No, I'll get to it later. First of all, I wanted to define the difference between these conditional value functions. We can define differences any way you want. Doesn't make any difference. Let's just do it with respect to the big J, the last alternative, just to set notation so we don't have to worry about it. So little vj is just the difference between conditional value function taking a little j versus the last j. So that is gonna, so we can define this CCP, we'll call them, just in terms of the expected value of the decision function, as Whitney was saying in the first lecture. And then what does that mean? Well, it just means that the value of the conditional value function plus the epsilon j has to be bigger than all the other ones. If you're differencing the big J out, well, that difference cancels out over here. So we could put it all in terms of the deltas. And so then if we, that is what this integrating over this G thing is. And then we're just going to, that by definition is just going to be the derivative of the, this is the distribution function for the epsilons. And what we're doing is, this is just the derivative of the G with respect to the epsilon J term. We get this formula here. That's just statistics, okay? Or definition of a probability distribution. So the thing that you should point out here, is that there are as many little p's as there are differences in valuation functions once you recognize the sum of the p's equals to 1. Okay, and so there are as many, for each x, there are as many p's as there are delta v's. Okay, and so you might think maybe these things inverse, maybe. Well, they do. To do that, you really need a functional form of the implicit function theorem, because you need a global result. So actually there is one out there called Hadamard's theorem, but there are several. And the basic point is that you can write the differences in the value, differences in these conditional value functions as functions of the conditional choice probabilities. Okay, that's what the theorem says. In other words, if you define this Q function as, well, what is the probability that I'll take action little j in a static model, where the systematic part of my utility is just a delta j, and then there's the plus the epsilon j. So exactly what Whitney was talking, that static model that going back to McFadden that Whitney was talking about. Define the Q that way, okay? It's just that probability in terms of those deltas, and then ask, well, suppose we plug in the Q's and the delta, the P's and the delta V's, do they match up? The answer is yes. Okay, so that's where we start from, and the point is that this Q thing really is just just depends on, well, it depends on the x's, and it depends on whatever assumption you're making about the unobservables. That's key, right? And everyone makes almost everyone, most of the time, makes the assumption that these are type 1 extreme value, and so that then is going to lead to a pretty simple form for the delta B's.
There's a really nice paper by Bertel's colleague Mons Foscarosh relating this to duality theory. And the social surplus function under these assumptions is strictly convex. The derivative of the social surplus is a choice probability. So therefore the Hessian is the Jacobian of the choice probabilities. And that's what you need to use the inverse function theorem to show that Jacobian is non-singular. Well, if the social surplus function is strictly convex, its Hessian is invertible. And so then you just use a very simple textbook inverse function theorem to prove the inversion result. So it's just a side comments. This paper by Foscarosh, we can put it on the Dropbox.
Sure, thanks. Yeah, the true proof that I have with Joe is a little bit more involved. Really, we should have been referring to Hadamard's theorem straight off. But there are, in fact, several ways of proving this inverse in function theorem. So it's true.
We're ahead of your time.
Whatever. The conditional value function correction, which I want to define now, is just the difference between, and this is the thing that Bertel was referring to earlier in a slightly different context. Looking at the ex ante value function versus the conditional value function. that turns out to be a fairly important thing. Obviously, this is what it's this is derived. We can define it for a non-stationary setting or a stationary setting. Suppose and one interpretation of thinking about this is suppose you decided to take action J before you saw the epsilons. Well, that's not optimal, obviously. You want to have a look at the epsilons first. And so you're not going to make as much. And therefore, you're going to lose a little bit. Okay. And the amount you're going to lose is that much. Okay. Now, so the loss that you're going to entail in doing that is just equal to this, what we're calling the psi minus the expected value of epsilon. So in fact, and this is not true of the type 1 extreme, by the way, but if the expected value of the epsilon was equal to 0, well, then it would be equal to the difference in that value between those two value functions. So that's just a little bit of intuition to explain why we call it the conditional value function correction. Okay, yeah.
I'm just a little unsure about the notation here. This capital V means the value function of the choice we actually took.
No, this is because notice it only depends on X. And so it's the expected value, social surplus, of what happens when you see the X. You haven't seen the epsilons yet, but you know that you will choose the optimal value after you see the epsilons. And so you take the, okay. All right, so here's one example of it. Suppose we had a bunch of GEV distributions. You referred to those briefly, and in particular, you did talk about what happens when you've got nested logit. In that case, when you've got nested logit, the value function correction is going to depend on something that depends on both the probability of choosing the nest, okay, and the probability of a particular choice in the nest related by the correlation between the correlation or the sigma, if you like, that fits in the nest itself. Okay, the degree to which there is correlation within the nest itself, and so that's a sense in which it's relatively easy to extend most of what's done on type 1 extreme value to the case in which there are multiple nests. I want to turn now to one way or the way in which we can use this value function correction stuff, because it turns out that we can think about expanding the value function into a bunch of terms that allow us to get out of the maximization thing altogether. After all, the people in the data set have already solved the maximization problem, so why do we have to do it as well? And then say, well, okay, that'll give us a simple representation of the value function that then allows us to do the estimation. We'll see how simple when we get there. So conditional value function can be extended just one period ahead by taking, say, the jth action. Okay, that's how it's defined. And then what we could do is take next period's v, cap v, and expand that out one period. Okay, because it's just equal to the conditional value function for any k. Notice that any action k, not just one action, but any k, arbitrary, not the one he took or anything like that. Any of the k's, and then expand that one out, okay? But you could just keep on going like that, or, you know, with the little vk, then just go up to the top line again and keep on going. And you can see how when you do that, you're going to get the k thing involved, okay? Because or you'll get one utility involved here, but sorry. Here we go. You get one of these utilities along as you expand this out, because you get, you know, when you expand this one out, you get another one, and then you'll get the psi correction. You get all these psi corrections as well. And then you just go out infinitum. You've got a beta discounting going on here. So eventually it'll die out, you know, contraction mapping theorem, whatever. And And in that way, you've got an expansion that involves the conditional value functions, use that you pick out to infinity, and size that you pick out to infinity, and then you're done. So to be a little bit more explicit about this, we actually could pick combinations of these things. These are the omegas. I won't go into a whole lot of detail. They don't have to be positive. They could be negative, but they do have to sum to 1, because really what they're relying on is this identity, okay? Because we're always expanding out this, sum up a bunch of these, provided they sum to 1, weighted here, sum up to 1, we're good. And then you can see that we've got the utility for this kth observation multiplied by the weight that you put on it, and taking account of the fact, well, if you take a particular choice, how is that going to push the state variables forward? Well, this is how it's going to do that. The state variables are going to be pushed forward according to this kappa function. So this kappa function is showing what is the distribution out of the state variables out at tau plus 1 when we start out at t, take action j initially, and then use these weights all the way out there, okay? So this is something, notice, that is simply worked out by looking at the f's. You pick a bunch of weights, and then that'll determine the distribution, and you go from there. I'm going to come back to this kappa later on when I talk about finite dependence. That's why I'm mentioning it now. Let's talk about identification now. Whitney mentioned that identification is really key in all of these problems. I absolutely agree with that. And the identification is always going to be in relation to the structure that you start out with. So we can talk about identification in structural econometrics models. We can talk about stationary identification in auction models and what we're assuming about the number of players that we're competing against with a computer, and various and what people know at the time. And then we're looking at what's our data look like, our data generating process. How does that data generating process relate back to the primitives that we care about? So that's why there's a fair amount of literature on this, on identification of structural models, of dynamic discrete choice models, because a fair bit has been written on it in terms of estimation. Well, first thing we should note is that the policy function is identified straight off. Okay, if excuse me, we know what the Q is, which really means if we know what the G is, if we know what the distribution from which the unobserved disturbances are drawn, if, okay? Because then we can write down, well, this is by definition what the policy function is. We can write it down in terms of these delta V's. We've got the inversion theorem. And so providing we know the Q, we're good. So if G is known, and the data generating process is something like this, which is what we usually assume, a bunch of state variables, a bunch of choices by people. And then the question is whether we have a panel or whether we just have the start and the end and the cross. In that case, you've got the policy function identified. Notice it exploits the inversion theorem to do that. Okay. Next thing to notice is that the conditional value functions also identified. So we can write, and you can see that because you can write it out. And here I've sort of just written out the set of equations. You don't have to follow them through right now, but basically I'm taking the V's and then I'm expanding them out with these weighted by the probabilities, and then just checking each of the pieces for the epsilon. This part we know about, we just talked about. And then the epsilons, we're integrating over those epsilons. So now you can see that that's just an integral of the epsilon times the optimal stuff. And that, of course, brings us right back to the Q's. And so again, the value function, the value function correction terms are also identified. Okay?
But not the value function. Specific value functions are not, because they're only difference that they're.
I didn't say I was.
Okay.
I just said the value function corrections.
Right?
Thank you. And so let's And so we have to go one further, okay? Suppose, sorry. Suppose we know the capital T, infinite or not, and we also know the discount factor, and we know the density, the joint density, okay? And in this setup, with our data generating set, F is also identified, okay? So we seek to identify it off the data generating process, okay? Now, that representation result that I gave you can be twisted around a little bit, okay? Just to go back to it here. See how we've got a V here and a U here. Now we want to subtract VJ from VU. Okay. Oh, sorry, VK from VJ, UJ from UK. We're going to have subtraction terms messy here. We can do that, okay? And then we'll get UJ minus UK. We'll get BJ minus BK over here. And this is getting back to John's point, it's killing my slides. What we end up is UJ, say minus U1. Why don't we do U1, okay? Is equal to all these psi terms here, psi terms here. We know the psi terms are identified. Suppose we normalize one of the payoffs for each state and each time period. One of the payoffs for each state. And we can call that one action one. We could call it anything we liked, and then we would just renotate here. But call the payoff that you're normalizing really the payoff that you know. That's what you're really saying. For example, maybe if the firm liquidates, they get 0, or maybe they sell and you see the number they sell at. So you know that, okay? You know that. In that case, all the other UJs are identified. And that is the identification result. And that is what John was trying to getting to before I stopped him. When he was talking about you only see the differences, you don't see the whole, you don't see the whole lot. Subject to that, you are getting what's called exact identification. Let's be clear about that. You have as many P's as you have U's. So if you efficiently estimate the P's and you don't impose any more assumptions on the U's, then you get exact identification. This is going to yield the maximum likelihood estimator. In other words, the only way you get more efficiency in any of these models is by imposing additional assumptions on the U's itself. And so you know, for example, that Mr. Zerker has linear payoffs in the repair costs or whatever, or something along those lines. Nothing wrong with making assumptions. And this is where I would, if Whitney was here, I'd take a little bit of objection to him talking about right models. Sorry, I lost that a long time ago. The issue is, which wrong model do you use to help you get a little bit further on a question that you'd like to answer? And that's my more limited goal. And I'm sure that's what he'd agree with too, by the way, if you had a chance to talk. So these are exactly point identified. And of course, there's a stationary one, stationary.
Your point identifies subject to the assumption you know the utility of at every state for one of the.
Correct.
So like in the liquidation example, if it depended on the state of the economy and you didn't know if it's higher than a recession and a boom, then you don't know that you won, right? So then it's not strictly identified. That
situation is even worse because the situation that you've described is one in which the state variable is unobserved. And I'm already assuming that I actually can actually observe the state variables. So if you introduce additional unobserved heterogeneity of the sort you're talking about, well then this result does not apply. And so you would have to, and then wait. and then in that situation, you would have to make additional assumptions in order to be able to get an identification of that model. Now, John wanted to correct himself just then by saying, well, suppose you do understand what the state variable is and you see the state variable, and it's just that the liquidation payoff that you see in some states is not only seen in some states, but not in other states. Just as bad. Because in that situation, even though it might be a stationary model, because you're not seeing the state variables in all the states, you have what's called a short panel. And so in that kind of setting, again, you have to make additional assumptions in order to identify the model and hence be able to get somewhere. That's not a bad thing. You work with the data you've got. The point is to try and understand the limitations of the models that you got so that you can then be more or less confident about what kind of questions you want to ask and also where you want to go from there. Okay? Good.
Thank you. Yeah, I agree with that.
So where are we? Yeah, estimation. Yeah, took as much as you want. Suppose we go with this unrestricted setup. Okay, so we're moving into the unrestricted model now. We've got the choice probabilities here. Okay, and then we can get the kappas from it. Okay. With the G, the big G, will then form our psi functions. Go from there. And we have the unrestricted estimates of the U's. See what we could do if you had, if you didn't know what the big G was? In that situation, you put in maybe a parameterized G. Let's not go too far here. Let's relax the type 1 extreme value, but let's put in a couple of parameters. Maybe it's normal with a few parameters or something. Get the correction factor for that, which you can do numerically. Plug that in there. Now you've got some parameters in there. Maybe if you've got some restrictions on the U's, well, then you'd exploit the restrictions on the U's that you've got in order to be able to estimate something about the unobserved heterogeneity. See the trade-off? Because I said that those conditions that I had before are exact equivalences between the number of P's and number of U's. It's exactly identified. So if you want to relax something, you've got to impose something on something else. But you can't do it, and we all do it. We all put lots of restrictions on the U's when we estimate these models. Think about a static model. We put linear, one coefficient on a bunch of x's that are moving up and down and just say it's linear, okay? We'll do that all the time. So there is scope for thinking about trading off where you're going to put your restrictions. Do you want to restrict the utilities, or do you want to or how much do you want to restrict the unobserved distribution? Okay. So in practice, here's what we do. We take a parameterized function of the current utility. We take a parameterized transition. So the model is now effectively defined by the time horizon, the discount factor, and that discount factor, whoever asked the question last time around, is going to be specific to the problem that you're dealing with. Not just to the time horizon, but it is very obviously specific to that, but also even to the application, because are you really trying to say something about the whole world? Shouldn't we give up on that and do something a little less ambitious and talk about the relevant discount factor for this particular situation? We've got the thetas that characterize the transitions and also the preferences. And in fact, in many applications, beta is known, U is going to be linear in X often, and this is sometimes degenerate, okay? Or people know it, okay? So one approach just go ahead and estimate this thing as best you can off the transition straight off. Limited information, maximum likelihood. Why not? It's often what people do, in fact. Then estimate the thetas. And somewhere in there, I should have said estimate the conditional choice probabilities as these, well, I did say it back here. Estimate these things. Okay. Plug them in here. Here's our unrestricted estimator. Sorry, here's our unrestricted estimator. Here's our restricted estimator, minimized with respect to that theta, standard minimum distance estimator. Plug in any old weighting matrix and then think about the optimal one afterwards. So you can also see that if this U is linear in theta, which it often is, that's a linear quadratic optimization problem, has a closed form, obviously. And so you would just write this out in the usual x minus 1 exponent y use notation. Okay. At a minimum, question?
No, I'm just trying to process something in my head.
It's all right. It's all right. Just to repeat, we have the unrestricted estimates. U is the current payoff, typically linear in the thetas. We do a minimum distance estimator by stacking these U's, you know, each T, each U. It's just a stack vector of the UJTs. And then we're taking this quadratic. Okay. Getting a closed form solution by writing it straight out. We know it's consistent. We don't have to search over the whole space. You might not like the efficiency properties, which are coming from the restrictions that you're putting in. You can actually do a test to see whether they hold or not. And then you can go from there.